Okay, let's begin lecture. And let me begin by saying welcome back from spring break. I had a great spring break. I feel like I've been gone for a month. I forget all my passwords and I didn't do a single you may have noticed I didn't really do a whole lot of stuff, hardly a lick of work in your guys' website. Although I did go up and get all your printouts on last Tuesday or something like that. But it's nice to see everybody back. Although I do wish that we had another week of spring break. Wouldn't that be nice? I mean, a vacation, traditionally, William, it's 2 weeks of vacation, right? 2 week vacation in Florida. All right, I'm in Florida, but I didn't get 2 weeks. Hopefully they'll figure the error of their ways and change that. Okay, our main topic for today and then part of tomorrow is angular momentum. We'll talk about torque today. We've handed back exam 2 printouts, and unlike last exam, the exam blurbs are already up. Also, there's a blurb for the clicker items, and that is up in web courses on the blurbs page. So you can. I went a long time before getting the blurb pages up for exam 1, but these ones are already up, so everybody's squared away with that. Some news and announcements. First is I finished a new chapter for the e-text. So it's not going to be in the one that you purchased, but I'm going to give it to you for free. It's called Chapter. I didn't give it a number, so I just called it Chapter X. It's going to be the new Chapter 5, but I don't want to mess your guys' minds up too much. So we'll just call it Chapter X, Angular Momentum, and it will be available in web courses today as soon as I dismiss lecture. It's in there. I've loaded it up into web courses, and I'll put a link on the homepage for you to look at it. This is what it looks like over here. This is the first page of it. I'm trying to make an EPUB version of it, so if you want to use your Nook or iPad or something like that. But I was hoping to get it done last night, but it messed up pretty bad. It's my software, my word processing software doesn't handle EPUB very well. So, but I'll try to get it squared away and to you as soon as I can, if you want to use that. Anyways, PDF should work, and you can print it out or do whatever you want. It's about 20-something pages, and the only difference being in what you're going to get, the PDF you're going to get has public domain images like this one, and with permissions and diagrams that I've made. And the one that is going to be published will have some stock images that the textbook company has to purchase and insert. So I put in substitutes. Like there's a picture of an ice skater in there that I downloaded from the internet, and it'll do until we get those other images from the stock photo company, Shutterstock.com. Anyway, so you can, and I want you to definitely, as soon as I publish the link, it'll be on the front page. Probably I'll put it also in the homework that you'll have tonight. We'll have a small homework. Anyways, as soon as you get it, just definitely read it. It should read fairly quickly. Lots of diagrams in it. That's the way I think. I think in diagrams, so there's tons of diagrams, not a whole lot of writing. But okay, now I want you to pay attention to the person in the lower left corner of this image that happens to also be sitting right up here in the front. That's Caroline from last semester in one of her SSG sessions. Okay, so I want to talk about SSG because we now have 2 exams on the books, and we can make decisions about how that's going to work. So we'll begin working out the SSG process this week. You can take a note of what it will entail. First of all, I have to send out invitations. Now, those will come to you in web courses if you are one of the people that have an exam average at 90% or higher. Okay? And so keep an eye on your messaging system, the inbox of web courses. And then you'll have to respond. If you get one, you'll have to respond to it, RSVP, and then I'll have to read it. And then from that, you'll be telling me what you want to do. You'll be figuring out a schedule for the 2 days prior to Exam 3. Exam 3 is a Thursday coming up, and first week of April. And so the SSG leaders will tell me where and when they want to meet for 1 hour, and then we'll set up a sign-ups page in web courses. Now, this is going to take a little bit of time. We should have the sign-ups page ready, hopefully the weekend before the exam. So the exam is going to be on Thursday. Then we'll have lecture Tuesday, but hopefully you'll be able to sign up before lecture on Tuesday, because after lecture on Tuesday, you'll start having SSG sessions, depending on your SSG leader. And so we want to try to get all that stuff set up and ready to go. It's a pain in the you-know-what, but over the years we've figured out how to make Canvas do what I want in this area, but it's not. And the other thing I want to mention to you directly at the front, at the beginning of this process, nobody is promised a spot in SSG. It's first come, first served. Okay? And there's never enough spots. Everybody likes to get the extra study in because it helps you do well on the test, and you get 4 bonus points. But that is guaranteed to no one. If I set, and I have to set it up for hundreds of you to be able to get in. So if your schedule doesn't allow you to get signed up in time, it's just one of those things that you're going to have to go with. You're going to have to go with the flow. And every semester, we have students that make a big ruckus. Oh, well, I don't think it's fair that I didn't get a chance to sign up for SSG. Well, if it were something required, then I would have to make sure that it's fair, that everybody gets a shot. But it's extra credit, and it's a finite resource. We can't offer it to everybody. I'd like to be able to say everybody can get into SSG if they want, but we never have enough SSG leaders to get, 6 students to work with every SSG leader in their session, and never and not miss anybody. So just so you know ahead of time, I wish I could make it more available to everybody, but we just can't. We try to make it available to the maximum number. And you guys that do get an SSG invitation to be a leader, you don't have to accept it. If your schedule is ultra busy, I know that happens for people, you can turn it down. And every semester there's 1 or 2 students that, yeah, Dr. B, I just can't fit it into my schedule. Even though it allows you, if you do it properly, to skip the final, some people still, I just can't fit it in for whatever reason. So Now, questions about SSG before we go on? May as well pause. Hector, you got a question? Last thing to mention about the exams, I'll be posting or publishing your Scantron score that corresponds to your printout sometime this afternoon after class. It's already in there, but I usually publish it and make it available to you on your grades page after I hand out printouts. So that plus your clicking add up to your total your total exam 2 score. By the way, if you got, I was handing out exams up here, and whenever I see somebody get, score above 30 on the Scantron, that means they have a C, no matter what happens with clicking, at least a C. Because it's a 50-point test, and if your Scantron brings you a 30, okay, you at least have a 60%, that's a C. And if I see somebody with 38 or higher, that means their Scantron alone has parked them in 75% or better, and that's a B. And so that's good, all right? Now, if I see somebody up in the 40s on a 44-point Scantron, then I get really excited because I know they're crushing things, okay, which we had at least one student crushed it that I handed it out for. I don't get, but the other thing is, if I don't say anything to you when I give you your paper, it doesn't signify anything because I just got back from spring break, so I'm even more clueless than normal. And 2, I don't look at everything as I look at the names, and sometimes I glance at the score, but I don't always glance at the score. So I might hand you a hot test, and I don't realize it. I just hand it to you and smile and say thanks and stuff like that. But that's the exams. All right, let's get down to business, angular momentum. This is the cover image for that chapter, and it's a lovely photograph from an observatory down in South America, Chile, a place called Paranal, way up in the Andes, the high altitude desert up there in Chile, which is like a perfect place for an astronomical observatory. Anyways, those curved trails, this is a time exposure. So you turn on your camera, you open up the shutter, and then you let it record the image for this one, I don't know, it's maybe an hour. Okay, those streaks are what the camera records for an hour for each star, and the star appears to move along a circular path. Now, that is deceptive. The stars are not moving on a circular path. What's moving on a circular path is Earth. Earth is spinning. This is a picture that's looking north through this complex. These 4 buildings here are 4 ginormous telescopes, and they use them all at once, kind of like binoculars, but this would be fornoculars. And they use them all at once to observe a certain star or star formation or galaxy. And because the bigger the light gathering area, the fainter the star, the further away you can see an object. So that's what they do with this. It's called the Very Large Telescope at the European Southern Observatory. And there's the credit for it. It's Alberto Gizzi Panizza from Italy, I guess. One of the researchers up there took this photo. It's lovely. That website, just type in Paranal and stars, and you'll get any number of pictures that just knock your eye out. Anyway, it's a good image because it communicates the idea of spinning and circular motion. One of the things I want to talk to you about is the concept of torque. And mainly what I'm going to talk about today is concepts that you can read about in detail in the chapter that I just completed and that you'll be able to download tonight from Web Courses. Torque is different from force. A torque that you provide, you can think of a wrench as providing a set of forces that cause a nut to twist and hopefully tighten or loosen up, depending on which way you're trying to spin it. A torque is a single force, or in the case of, a wrench here, the wrench, this opening of the wrench applies force to that nut all along this surface. So there's a lot of newtons, small forces applied to the nut over these two flat faces over here. Same thing down here. Now this is a 1/2 inch and this is 9/16. Typical wrench, open-ended wrench. And the amount, if you have a nut on a bolt that is really tight, sometimes you can't get it off with your hand, and so you got to get a wrench. And why is a wrench useful? Well, your hand can, if it's not too tight, a lot of times you can twist it off, get it going with your hand. But if it's really tight and locked down there real tight or even rusted on, you need a wrench. And that's because with a wrench, Celine, you can put some force onto the wrench way out here and turn the nut at the other end over here, and that extra distance gives you leverage. So make a note to yourself, leverage. Leverage is the informal term that corresponds to the precise physics vocabulary term, torque. A torque is a force acting over a distance, and a good prototype of it is just the wrench, what the wrench does. So if you're over here at the 1/2 inch end of this wrench and you exert 5 newtons, that's going to cause a little bit of spin. Hopefully you can break the nut loose and get it to go around and loosen it or tighten it. But if you do 5 newtons over here in the middle, that might be enough. You might not have to go all the way out here. Now, if you've ever seen wrenches, they make some big, wrenches this big. These open end or crescent wrenches. And we had a guy when I was in grad school. There was a guy that worked in one of the labs, and in the lab they had all these plumbing lines that were designed to create a vacuum. They were basically doing stuff that big factories use to fabricate electronics. They were doing it in the lab. They were developing new techniques and stuff that we now use for manufacturing electronics. And to do that, a lot of the procedures, you have to have a vacuum. You do all your lasers and all your gold depositing and stuff in a vacuum, as close to a vacuum as you can. So you have all these big pipes, and they're all really low pressure. They're evacuated. They're vacuums, right? And so because they're a vacuum, stuff can get really tight because the air pressure will, tend to push things inward into the vacuum. So if you have a vacuum inside of an enclosed container, it can be mighty hard to pull apart. So there's this one guy that worked out in that lab, and they had this wrench that was this long. I swear to you, it was this long. And he was putting so much torque. He might have taken a steel pipe, and you know what you do with a a wrench to get even more torque on the wrench can give you, you put a pipe you slot a pipe onto it, and then you get to the end of the pipe. And then the pipe puts torque on the wrench handle, and the wrench handle puts torque on the nut or the bolt that you're trying to work, and hopefully you get it to spin. So this guy, it was infamous because there's this gigantic wrench, right? And he was putting so much torque on it. This beautiful steel. You know, they make these things with really tough steel. I mean, the good wrenches, the good tools. So he had this big crescent wrench, you know, made of steel, you know, high-grade steel, and he broke it in half. He put so much torque on it that and so they started up this annual grad student award, the Excessive Force Award, for the year, you know, 1994 or whatever it was. And that guy, he was the inaugural, and he actually broke a big monster crescent wrench in half. It was impressive, really, you know. Now let's take a look at some of the other things that happen with rotational motion. Here's the thing that torque provides. Torque will start something rotating or spinning. All right. Now, regular F equals ma forces, if you apply a force, as you'll read tonight in the PDF, if you apply a force exactly at the center of mass, you'll cause the object to go from point A to point B in a straight line, or accelerate anyways, from point A to point B in a straight line. That's called linear motion or translational motion. Okay? And if you apply the force slightly off center, slightly away from the center of mass, it'll tend to spin one way or the other, depending on which side you're on. So 5 newtons on the left side might give you some clockwise spin. 5 newtons on the right side might give you some counterclockwise spin, but it'll get you some spin one way or the other. Now, if you, for instance, toss a wrench, you know, like that one we were just looking at, it's not a perfectly symmetric object. It's got more mass at one end than at the other. So the center of mass is not in the exact center. But if you toss a wrench, what you'll see is the center of mass will follow a trajectory like this dotted line up here. Okay, a parabola. That's the center of mass. And then the wrench will spin around. So if you take the end of a wrench, you know, and go, you know, toss it like this, it'll go end over end. But the center of mass will have a very precise trajectory. All right? And so as it's moving along that parabola, just like a baseball would. Matter of fact, a baseball, you baseball guys, are you pitchers? Okay. The guy that's not paying attention? Okay. By the way, we got to have a little discussion after class because of the mess up. Anyways, a baseball pitcher, you know, when they're trying to put throw a curve ball and deceive the hitters of the other team, they put some torque on it as they throw it. So that thing's spinning as it's moving along a fairly shallow parabola, just like this. So it's not like throwing a stick. You know, they're trying to put a different kind of spin on it than you would if it was going end over end. This thing's going end over end over here, right? But you can have a combination of both motions. You see it every day. Matter of fact, whenever you see a football game, okay, the football, you know, the place kicker, he won't kick it normally at the very center of the, he'll get the lower part of the football with his foot, okay? And what he does with that, he sweeps down with his foot and he lofts that football toward the goalpost. And because he's striking it off center, below the center of mass, it's also going to spin. And that's the end over end motion. Unless he really catches it sideways or something, then it kind of goes like a floater. But if he's in good form, it's going to go end over end. Another example of parabolic trajectory for a football with spin is not end over end, but a good spiral pass. Okay? Another example, punters in a football game, they'll try to get usually, I mean, if they're trying to go for distance and height and hang time, they'll try to put a spin on the football so that it goes through a nice spiral motion. Now, they don't have as much directional control as a quarterback throwing it with his hand, but it's very similar. Okay, so a spiral motion, spiral pass, or a punt, a good punt for distance and hang time, and then football, end over end trajectory. Now let's go to the next slide here. All right. Now here's a simple rotating object. Okay. And for instance, you have a kind of a disc-shaped object, and it's going at 600 RPM. That's normal. 600 R. There's all kinds of machines that go at that speed. It's pretty fast, but I think that's slower than your disk drive in your computer. But so the rotational analog to regular momentum, linear momentum, or translational momentum is angular momentum. You can have something that's spinning like a top, and it's not going from point A to point B. It doesn't have any linear momentum in that sense, but it has spinning momentum because all those grams of mass of the top are actually spinning. So they have some kinetic energy and some momentum. But where 1 gram is going to the left, if it's spinning, another gram is going to the right. When 1 gram is going forward, another one's coming back the opposite way. And they're on opposite sides. And because they're all connected by mutual intermolecular forces, it holds together, doesn't fly apart, and it spins. Okay? And so angular momentum is the analog to regular momentum, P equals mv. The rotational analog to F equals ma force is the torque. And a common symbol for torque is the Greek letter tau, lowercase Greek letter tau. And this is a Greek lowercase alpha, and I is something that you'll read about in your textbook. It's called moment of inertia. And we'll talk about moment of inertia a little bit here. Okay, so here's the basic second law. F net equals delta P over delta T. It is the time rate of change for the linear momentum, the translational momentum, and that is Newton's first law. That's what pushes and pulls do. All right? Gravitation is a pull force, and it will not provide any torque, but it will provide some change in the momentum state and some force. Now, the rotational analog to Newton's second law is simply this. It's the change in the angular momentum with respect to time. The symbol for angular momentum that I use is capital L. Some textbooks use capital S for spin angular momentum, and some use capital J. Yeah, those are question marks up there. So yeah, this is the, oh boy, that projector's a little bit off center. Wow. Somebody bopped those two projectors. They're a little bit off center. I'll have to remember that. Yeah, so this is a question mark here, and this is delta T down in the bottom. Okay, and there are two kinds of angular momentum. So delta angular momentum over delta T, that's going to be my torque. that I get from a wrench or just my hand grip, the vice grip like hands. The first kind of angular momentum is called orbital angular momentum. And that's the momentum that an object has as it moves in a curved path around a central point. So for instance, the Earth going around the Sun on its almost circular orbit has angular momentum. The Moon going around the Earth on its almost circular orbit has angular momentum, orbital angular momentum. And that's because on your orbit, you don't really go from point A to point B. Well, you go to point A to point B and then back to point A and then you go around and around. So it's hard to say that there's a net translation. You just kind of repeat it. And when that's the case, angular momentum is a factor. Another factor, another kind of angular momentum, is called spin angular momentum. And in the textbook, the PDF chapter that you'll be able to look at tonight, I mostly talk about spin angular momentum. Spinning wrench, spinning top, spinning Earth. Earth spins on its axis, so the spin angular momentum of Earth is a different number than the orbital angular momentum of Earth. There's two different flavors of angular momentum. Now you can add them together because they're both angular momenta, and that would be the total angular momentum of the Earth on its orbit. The Moon spins once every orbit. Not by design, but because it gradually slowed down its spin to synchronize with its orbit. And so now one orbit, one spin is what you get for the Moon. And that's why the Moon is always facing the same face. The same face of the Moon is always looking at us, the man in the Moon. Okay, the far side of the Moon is always faced away from Earth, no matter what what part of its orbit it is. But the Moon does have spin angular momentum. Now let's do some pictures for spin and orbital. And it looks like my outline is misnumbered. Start this one number 1, orbital angular momentum. Here's the formula down at the bottom, L equals mRV. And that is, go ahead and make a note, orbital angular momentum is the mass times the radius of the circle times the orbital speed v. And students, that is for a circular orbit. And Earth's orbit around the Sun is very close to a perfect circle. Technically, it's a little bit elliptical, but not by much. So there's some fixed point of interest, and r is the distance from that point out to the object that has orbital angular momentum. And so here's the Sun, this kind of greenish, yellowish sphere here. That's the Sun. Here's the distance from the Sun out to the planet, and that's planet Earth. You can't hardly tell, maybe, but that's a little miniature version of the Earth. And the velocity on that orbit times the mass of the Earth will give you the orbital angular momentum. Now, you can do a similar calculation for a comet on an elliptical orbit. Go ahead and try to sketch that in. Because a comet will, on a highly eccentric elliptical orbit, it's just obeying gravitational forces from the Sun, but it has a different velocity state. It's got a different angular momentum state, but you can calculate the angular momentum for a comet. Now to do that, you'll use a lot of trig and a little bit of calculus. Well, quite a bit of calculus. So we're not going to do an elliptical orbit, but you can there is one thing that you can say about an elliptical orbit, and that is the angular momentum is conserved. It is always the same for any gravitational orbit. Go ahead and make a note of that. The orbital angular momentum is conserved for any gravitational orbit. Now, on a circular orbit like Earth, that makes sense because you're going the same speed all the way around a circle, so MRV is the same. But now, out here, MRV is different. Excuse me. R is way different out here on the far end of this ellipse. So make a note to yourself. Put a dot out here at the far point of your ellipse. That's a point called, I don't have it on the diagram, but I'll spell it out for you. It's a point called aphelion. A-P-H-E-L-I-O-N. Aphelion. It means away from the sun, the furthest point from the sun. So this baby out here, aphelion. And you can compute the angular momentum there. And the cool thing is, if you go down here to the closest point, this one down, go ahead and make a little dot down here on the ellipse at its closest point. That's the point called perihelion. Let me spell that for you. P-E-R-I-H-E-L-I-O-N. Perihelion. And William, one of the things about perihelion is, down here, if it's a gravitational orbit, it has the same angular momentum down here. But check this out. R is smaller down here. R is bigger out here at aphelion. So make a note in your diagram. Large R. R is big. It's way far away from the sun. And down here at perihelion, make a note. Small r. It's close. That's the closest point. Now, I want you to look at this formula here. If you have the same amount of angular momentum at both points, and if the mass of the planet has not changed, but r has gotten bigger, then v has to be smaller by exactly inverse proportion. All right, so r and v vary all the way through the orbit in such a way that L is always the same. So big R at aphelion, small v. So make a note of that out here at your aphelion point. Big R, small v. L equals the same. And then down here at perihelion, down here at the closest point on your ellipse, small r, big V at perihelion. So ask yourself a question. Where is this comet moving fastest? Down at perihelion. Small r, big V. Matter of fact, small est r, big-est v. That's where its maximum speed is. And this is biggest r, smallest v. This is where it's poking along the slowest out here at aphelion. Alexis, question. Yeah, perihelion. Yeah, well, this is a perspective view. We're looking at it in perspective. So we're kind of up above the plane of the solar system. Okay, so it's like if the solar system were traced out on the floor, we're kind of looking at it from, 5 feet up.
Okay, my other question was, L is the abbreviation for orbital angular motion.
Orbital angular momentum. And I use it for spin angular momentum. But this is the formula. You don't use this formula for spin angular momentum. You use it for orbital.
So what does L actually stand for?
Angular momentum. Either kind. Okay? All right, and I hope this makes sense to you because down here go ahead and make a note. Perihelion. Boy, we're loading up your diagram. Hope you still have some room. Perihelion, you're in close. R is smallest. Gravity is strongest. Gravity's really pulling you in. You're getting whipped around the back side, the near side of the ellipse. You're really whipping. Out here, gravity is wimped out because you're at bigger R. Remember, in universal gravitation, R squared is in the denominator. So if you have a big R, it's in the denominator and it's being squared. So increasing R weakens the gravitational force. So out here at aphelion, make another note, weakest gravitational force. And then in here you've got, between aphelion and perihelion, you got all those intermediate states, and that's where you really need the trig and the calculus. But perihelion and aphelion, yeah, you can hack those pretty good. All right? The MRV will be the same at each. The product of M, R, and V, even though the R's won't be the same and the V's won't be the same, MRV will multiply out to the same at both points. All right? Now, another object that has orbital angular momentum is an electron as it orbits the atom. So make a note of that. You have to know your fixed point of interest, the sun or the nucleus, the distance out to the planet or comet or electron, and the velocity. And if you know the velocity or the speed, you can figure out L equals mRV. And for an elliptic orbit, it's kind of tricky, but you can do it. Circular orbit, it's not too bad. It's mRV. R is the same all the way around on a circle. So make a note over here for this circular orbit for Earth, the black one, make a note, R is the same all the way around because it's a circle. So V is the same all the way around because it's angular momentum conserved. Now here's your V. Oh man, drawing a tangent. See that, Alexis? I've got the tangent vector down here, but unfortunately it's going off the page. Sorry about that. These two projectors are both blooped up. Now, let's talk about spin angular momentum. I guess these are out of order. This is the one that's supposed to go first. Anyways, go ahead and number them the way you think is good. Now, the spin angular momentum is actually the sum of a ginormous number of MRVs for a rigid object. And because it's a rigid object, because it's a rigid object, they're all hooked together by intermolecular forces. It's rigid. In other words, it's not made of water. It's not made of jello. It's rigid, and so they all have the same spin rate, the same angular frequency, and so you have a bunch of orbital angular momentum. So just think of every pixel of this disk. Each pixel's got some MRV around this axis, and you add all those up, and you get. Now, as you'll read in the textbook, the formula for angular momentum is simply I times omega. Now, I is known as the moment of inertia, and this factor here, go ahead and make a note. The moment of inertia is the rotational analog of mass. For F equals ma, second law, the mass is measured in kilograms. The moment of inertia is measured in kilogram meters squared. And you'll read about that in the textbook. And That is because the moment of inertia encodes the resistance to the change of rotational state. So if something has a lot of moment of inertia, that means it's hard to spin. If something has a smaller moment of inertia, it means it's easier to spin. Now here's an example that you've probably seen on television. You watch the Olympics, you see figure skaters, and a lot of times you'll see a figure skater, they start to go into a spin. And then when they bring their arms in, they really spin fast. Or if they start with their arms in and they bring their arms out, they extend their arm, or maybe even their leg, if they're really good, then they slow down. Okay? And that's because they're changing, using their muscles, their moment of inertia. They're extending R squared for their hands and their outer arms, or their leg, if they're using their leg to extend, to slow down. If they bring it in, they're changing R squared to a smaller value. So the moment of inertia, as you'll read in the textbook, encodes this quantity m times r squared. M times r squared for each pixel, and it all goes into I. Now, I've figured out the moment of inertia for a couple easy things, a wheel and something called a rigid rotator, and then I've given you the results for a sphere, which has a moment of inertia, a cylinder, and a straight stick, straight object. Question? Rigid means you can't pull it apart, you can't smash it. Compact, it all rotates as one. So think about water. You wouldn't call water rigid, right? And if you take a pail of water and you spin it, the water it'll slosh around, and parts will go faster than others and stuff like that. But if you have the same pail filled with cement, solid cement that's dried, it'll just all go as one object, kind of like this one. Right? Now, the moment of inertia for electrons is a mystery. We do not actually understand why electrons have intrinsic spin angular momentum. We don't understand why they have structure. We don't think they do have a structure. We don't know what it is. We've been trying to figure it out for over 100 years, and we haven't figured it out. We don't know what it is. Neither do the Russians. And nobody's. What's that? Oh, omega. Omega is the angular velocity. And you'll read about that in your textbook as well. Now, so the interesting thing about electrons is they have spin. We don't know why. Photons of light also have spin. So there's a lot to really think about. There's something profound about angular momentum that we don't really have a fundamental understanding of. There's still a lot to learn, still a lot to think about. That's why I'm trying to teach you guys about it. Maybe one of you guys will have the insight, or maybe one of your grandchildren will have the insight to understand it. Now let's take a close-up look at this thing. Here's that same object, and it's spinning from this view. It's spinning anti-clockwise. And for a rigid bodhisattva, every point is going to go at the same angular velocity. So angular velocity just means so many degrees per second, or so many revolutions per minute, so many RPMs. And I explained in the chapter how to, the normal way of figuring out the angular velocity or angular speed. So here's your delta theta. Here's your change in the angle over here and over here. And it happens in the course of some elapsed time, delta t. So it's just the quotient of those two. All right? And because it's rigid, these two angles, delta theta 1 and delta theta 2, will be the same. All right? Now, I have a clicker question for you. Go ahead and get your clicker ready. And let me just make this last point that if you think about the speedometer rating of two different points, like this point right here, it's in close to the axis, and this one out here, it's a little closer to the edge. If you had a little speedometer for both points, this one would have a bigger speedometer because he's moving on a circle that has a lot bigger radius, and therefore every revolution covers more territory for this guy. This inner dot here, a point there, he's on a smaller circle around that axis. And so it takes the same amount of time to make one full turn. But this guy's, he's just going a shorter distance because he's got a smaller circle. So his speedometer in meters per second or miles per hour or whatever you want to call it is going to be lower. And for this point out by the edge, the linear speed, the translational speed, miles per hour, meters per second, is going to be bigger. All right? It's rigid, so both of these guys make one turn at the same time. They're rotating together. But one's covering less ground, one's covering more ground, the same amount of time. So this guy out here, he's got a higher speed. But according to the first paragraph up there, they have the same angular speed or angular velocity. That means if you think of degrees per second, not miles per second, not meters per second, but degrees per second, yeah, they're both the same. So angular velocity and regular velocity are not the same, and the regular velocity or linear velocity is different depending on how far you are away from the spin axis. Okay, but angular velocity, no, if it's rigid. So here's my clicker question for you. And I want you to really think about this carefully. We're on frequency BB. Two coins rotate on a turntable. Coin B is twice as far from the axis as coin A. So B's out there on a big circle. A is in here on a smaller circle. What's the relationship between their angular velocities? Go ahead and vote. Okay, 15 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys voted for. Ooh, look at this. A spread of answers. The answer is B. Now, option A, the angular velocity of A is twice that of B, is incorrect Option C, the angular velocity of A is half that of B. That is incorrect as well. But coin B does have twice as much, or coin A has half of as much of something as coin B has. What would that be? The speed, the regular speed, the linear velocity. So if I ask you a question about the linear velocity or the speed, then you'd want to answer down here for C. All right? Now, I'm going to dismiss you. Read the PDF. I'll link it in about half an hour. And I'll also give you small homework. If you didn't get your exam printout, come on up here to the front. And Miss Caroline will help you with it. So you're in charge of this. I'll get this.